In this video, we introduce a framework for edge computing in industrial operations. Let's start with a little background on edge computing and why the edge matters. More specifically, why is it used in the context of industrial operations? Edge, including sensors, computing, hardware, and software, is critical in industrial operations because it brings a new level of visibility and operational intelligence closest to the field where machines and people work. It does this at the speed of operations as work occurs. Industrial environments with distributed and often remote operations, such as the oil and gas industry, have typically suffered from lack of data, or in some cases, too much data, or data in silos specific to individual pieces of equipment or processes. Gaining useful and timely information and making decisions in such dynamic environments has been challenging, and operations has typically been reactive to unexpected changes. Edge brings new capabilities in synthesizing and analyzing relevant data and applying it to the context of operations in real time when decisions must be made. The powerful combination of edge computing with industrial IoT applications not only provides visibility and operational intelligence, but also drives real-time decisions at the speed of operations, leading to improved efficiency, productivity, plus worker and environmental safety in operations. Edge has many different definitions and often depends on your point of view. To put it all into perspective, here's a simple edge framework which is comprised of 6 different aspects organized into 3 categories: physical, digital, and functional. Let's start with physical, the sensors and hardware. This is where data is sourced, from sensors, which bring contextual awareness, to edge computing and hardware. Today, you can find sensors for almost anything, as they've become much more widely available and come in all types of sizes, shapes, and costs. There are thousands of different types of sensors and even more variations of each type. If we look just at pressure sensors, there are 15 different classes of sensors, such as piezometers, tube pressure gauges, tactile sensors, barometers, and many more. And even with piezometers, there are over 50 types and models: vibrating wire, pneumatic, titanium, etc. In fact, pressure is just one of the many attributes for which there is a whole sensor family. Along with these different models, sensors have many different characteristics, such as the type of technical or scientific mechanism and different calibration techniques. They can be analog or digital and are available in many different form factors. They use different protocols, formats, and wiring. Sensors are often built in or integrated into existing devices, systems, or equipment. Or they may be plug-and-play add-ons that provide additional data sources, such as temperature, vibration, or humidity, for example. Hardware includes batteries, sensor boards, physical ports for sensor connectivity and integration or communications and other electronics in a physical enclosure. In industrial environments, hardware is often hardened or ruggedized for harsh outdoor environments that may require extended operating ranges to work in extreme cold or heat. There is even explosion-proof hardware for certain environments such as natural gas facilities. Next, let's look at digital. Digital includes compute and communications, which enable the edge. Edge typically integrates compute and communications interfaces into the hardware. Smaller size, lower cost, and low energy consumption systems now make edge computing much more feasible with advances in compute systems and the wide availability of microcontrollers and system-on-chips. Previous challenges with powering edge devices in remote locations or distributed industrial environments make these new chips very attractive. Smaller sizes allow for very compact edge devices, as well as lowering the cost of the devices. A microcontroller is a small computer on a single integrated circuit that includes a CPU, memory, and programmable I/O peripherals designed for embedded applications. They can be used for data collection from sensors or sensing, as well as actuating physical devices. A system-on-chip is an integrated circuit with a CPU, memory, I/O ports, and secondary storage, with lower power consumption and small footprint, and usually have more pins and can integrate more peripherals than a microcontroller. Communications to and from the edge depends on hardware and software to transmit and receive data through local, short-range, or long-range technologies. Communications at the edge can be wired or wireless. In industrial environments, communications are often a challenge, with physical or geographic issues making wired connectivity difficult to implement. There are many different wireless communication protocols available, such as Wi-Fi, Bluetooth, Zigbee, LoRa, and LTE, which are common in industrial IoT implementations. Each of these protocols has their advantages and trade-offs in terms of data rates, range, power consumption, bandwidth, reliability, security, cost, and whether they are proprietary or open. Last and very important is functional. Software is the other key aspect of edge. Functional software is critical in edge IoT deployments with a software operating system to support the edge computer's basic functions, such as hosting and running applications and controlling sensors or actuators. Applications interact with the sensors and field devices. These edge IoT applications perform the integration, analytics, and prediction that are necessary to deliver operational intelligence. Most IoT applications are based on machine learning or some artificial intelligence-based algorithms to analyze the ingested data in context, create digital models, and run optimization scenarios. Edge software, such as an energy optimization application or fuel management application, deliver analytical insights and automate operations. Edge computing and industrial IoT applications bring real-time visibility and operational intelligence to industrial operations. Edge impacts industrial operations in three ways. One is information transformation. With all the data that resides on the edge, companies can gain a competitive advantage based on how fast they integrate, process, and analyze this data, turning it into real-time operational intelligence. Second way is commercial transformation. This operational intelligence from the edge also impacts the entire business in areas such as supply chain decisions when interconnected. Availability of more granular information gained in real time directly from the infrastructure and products themselves enable faster supply chain adaptation and decisions. And the third way is workforce transformation. Digital technologies will increasingly be a part of the front line of operations, challenging the workforce to step up their digital skills while enabling new ways to operate. For more information on edge computing and industrial IoT, visit the Atomiton website.